Yes.
Okay. Okay, so we are here again with Antonio and Armin as a special guest star, and they will talk a bit about the PyPy JIT interpreter. Yeah. Antonio.
Okay, thank you, and hello everybody. So let's start with the talk. This talk is divided in 3 parts. What is PyPy? But this will be very, very quick part because you should probably know by now. Then we will have a part which is an overview of tracing JITs, because PyPy is fast because it has a tracing JIT, and we will explain in general what are the concepts behind tracing JITs. Then we will talk more about the particular case of PyPy and which optimization it does, and etc. And of course, since we are a lot inside just-in-time, this is also just-in-time talk. We finished 10 minutes ago to do the slides. So what is PyPy? Well, basically it's divided in 2 parts. It's one part is called the EuroPython toolchain, and it's a language. EuroPython is a language. It's a subset of Python which you can use for writing programs. In general, it's designed to be useful for writing virtual machines, because you get a lot of features for free, like the JIT compiler, the garbage collector, and etc. And you can use the EuroPython toolchain to write whatever interpreter you want. Python is just an example, but then we have JavaScript interpreters, Prolog, Smalltalk, whatever language you want. And then, of course, there is the Python interpreter, which is, well, the end goal of PyPy. And it's compiled using the EuroPython toolchain because it's written in EuroPython. As I promised, was 30-second explanation of PyPy. Part 1, now we will explain a bit what is a tracing JIT. But first, what is a compiler? Well, its compiler is something which translates the source code to some other target code. There are basically 2 main categories of compilers, which are the batch compilers, ahead of time, GCC and JavaC, or well, all the usual classic compilers you know. And then there are just-in-time. Just-in-time means that they delay the compilation as much as possible, and you distribute usually some directly the source code or in some intermediate code, and then the compiler emits the assembler code at runtime during the execution of the program. There are other 2 main differences between compilers. A compiler can be static, or what is called dynamic or adaptive compiler. The difference is that the static compilers can use only the information in the source code or in the intermediate code to generate the assembler. And a dynamic compiler has the advantages that it uses the information which you get at runtime. So, for example, it knows the type of the objects, or the value of that particular variable is 0, or it's greater than 100, or whatever. And of course, to be dynamic, a compiler must be just in time, because if it's ahead of time, we don't have any runtime information to use. But not all just-in-time compilers are dynamic or adaptive. Like .NET is a classical example, because it has a just-in-time compiler, but you could just run it earlier. There is even a tool to do it, I think. And it doesn't really exploit this ability. And then there is another big difference between in compilers and for object-oriented languages, a compiler can be method-based, which means we take a method or a class and we compile it alone, and we emit the assembler for it, and then when we call the method, we just call the assembler. Or there are tracing compilers, like the case of PyPy, which they really don't care about the division in methods and functions. They compile loops and they inline functions inside loops and etc. As you guessed, PyPy is a JIT compiler, is a dynamic compiler, and is a tracing compiler. What is the idea behind tracing compilers? Well, there's the usual 80-20 rule that most of the time of a program is spent in a very small part of it. We call this part hotspots, and the idea is that if we optimize very aggressively the hotspots, we get most of the speed we can, even if we don't optimize the other code, the slow code. And the other principle is the one which I call the fast path principle. So the idea is, again, we optimize only what is necessary, but we want to ensure correctness. So if there is a case which is very common, like you have an addition of two integers, usually they don't overflow. The addition doesn't overflow, and you can just build an int object in Python. But you want to make sure that it still works even if the result overflows and you want to build a long object. So we emit code that it's optimized for the common case, but it still works in the uncommon case. These two assumptions lead to the fact that we assume that most of runtime of a program is spent inside loops, and that each iteration of the loop always takes the same code path. Like you have a loop, we have some if and else and some branches, and we assume that most of the time you always take the same code path. Well, this is not really the truth, because there are cases in which the same loop can take more than one path, but usually the number of fast paths is smaller than the number of all possible paths. So, to go more in the tracing JIT area, usually a tracing JIT starts, well, an interpreter with a tracing JIT starts by interpreting the program as normal, like it does CPython. It's a normal virtual machine with bytecode and etc. and interprets the bytecode. While it does this job, it also detects hot loops. Every time we have a back go to an earlier place, we increment a counter, and as soon as this counter reaches a certain threshold, it means that this loop is hot because we have executed tons of time. Then we enter a special mode which is called a tracing phase, which continues to execute the program, but this time it records all the operation it does. So at the end, until the loop is, the end of the loop is reached again. At the end of this process, we have a linear trace. Note that since we really looked at what we execute, all the ifs and all the different code paths are linearized because you just go through one code path, one specific code path. So it's a linear trace. Having a linear trace makes things much easier when you want to optimize it, because you don't have to think about what happens if this condition is false and etc. You really have a very concrete code to optimize. After we have traced and optimized the trace, we can compile it to the assembler code, we execute it, and then we win. Of course, since this trace represents just a single possible code path, we need to insert what we call guards to ensure the correctness, because as soon as the loop stays in this code path, we are fine and we are fast. But if by chance well, sooner or later it will happen. One of these conditions is false. We want to go out of the assembler code and start interpreting again and well, do things slowly but correctly. So these diagrams try to explain what I just said in words. We start by interpreting the program. Then when we detect a hot loop, we start the tracing phase. Then when we finish the tracing phase, we compile it, and we start running. Then the code runs, we are happy. At some point, some guard fails. And so we go back to interpretation. If you look at the label, I put a cold guard fail because, well, it's the first time or the guard, that specific guard fails, so we go back to interpretation. Then at some point, we try again to enter the loop which we already compiled. So instead of going through the tracing and compilation steps, we can just skip directly to the running because we already have this code. And then what happens? After a while, we have a guard which fails, which means a condition we didn't consider in the first approximation. The code path we never traced, but it fails once, it failed twice, it fails 3 times, and then we say, okay, we should maybe try to compile it as well. So we go back in tracing mode only for this new code path. Then we go to compilation and running again. And then next time this particular guard fails, well, we can just stay inside the running phase. So after a while, you start with a program which is completely interpreted, and you compile one piece after the other, and you get, hopefully, some assembler code which covers all your most common cases. So now we do a more concrete example of what tracing means. I chose to use Java because to avoid confusion. Because in PyPy we use, as I said, EuroPython, which is our low-level language, to implement Python, up-level Python we call it. And but the syntax is the same. So if I just show you some Python code, you might be confused and think it's up-level code. So I just use Java, but the idea is the same. So here we have a very easy standard Java program in which we have an interface, a class which implements this interface, do something, doesn't really do anything interesting. If the parameters is less than 0, it returns x minus 1, else x plus 1. And then we have a loop. This is a loop, and inside the loop we repeatedly do the same operation. We always call op.doSomething, passing I, which is incremented, because it starts at 0 and then it's always incremented until the loop ends. If we disassemble the Java bytecode, well, I'm not going to explain in details what happens, but this is the Java bytecode equivalent to the source code I showed you earlier for the doSomething method. And well, we load the value of the variable. We check. This is the if. We check if it's greater or less than 0, and there is a jump in case it's not greater than 0, and etc. And it does an addition or a subtraction depending on the value. Nothing. Oops. And for the main method is the same. We have the loop, a label, the goto to the label, and there is this invoke interface. Oops. Invoke interface operation with just a method call, a virtual method call. And in Java, you don't know the exact type of the variable, and you can have any concrete class, so the compiler have to emit code to call whatever class we pass to. So when we actually execute the code in a tracing JIT, what happens? Well, we start in the method main. We execute. Well, okay, we are in the tracing phase, so it means that we already interpreted it for a while, and then we are at the point where we detect that the loop is hot. So we start tracing from the beginning of the loop, and then whenever we trace a line, we record all the bytecodes that are executed by the virtual machine inside our trace. So this iload 2, iload 1 are really these 2 bytecodes are executed and recorded at the same time. Then there is this if something then jump opcode. And then, as I said, in the traces, we don't want goTo's because we want a linear trace. So what we insert instead is a guard. So the guard, this particular guard is saying this trace is valid only if this condition is satisfied. So in this particular case, it's guarding that I is less than n. Then we start with the next line, which is the method call. So we load the object on the stack, we load the parameter, and then there is what invoke interface. And now our tracing JIT does something special in this case as well, because we really want to trace all the operation, and we want to go inside the function we call. So we just try to inline it, but then, as I said, it's a virtual method call. We don't know which is the exact implementation or do something. It could be everything. So we guard the class. Guard class means this particular trace works only if the object op is of the class inc or dec. If by chance later in the trace it arrives some object which has a different class, the guard class fails, and then we start interpreting again, and etc., etc. And then we continue tracing, and we are inside the do something method. And yes, okay, we continue doing the trace as I just explained. But the important thing of this slide is that we insert guards instead of conditions of if and goTo's, and we automatically trace inside methods. So we almost never record a call, unless it's some external call that we don't want to trace because, well, it's a C call or whatever. But we are not going to explain this. Also note that when we record the trace, we record the actual operations. So we also record the values of the operation. So iload 2 means loads the second variable in the bytecode, but when I execute it, it has a concrete value of 3. And when I load 1, it means load the first parameter, it has the concrete value of 100. And I record this in the trace. And then the optimizer and etc. can use this information, but in various ways. We will see it later how it works. This works as long as the trace is linear. But as I said, if a guard fails and fails often, then we want to compile more code. But then it means that we have the compiled code for the trace, well, the compiled code for the guard which failed, and we want to connect them somehow. And what we do is to insert a jump. The guard has failed, okay, jump to the compiled code, the newly compiled code. And after a while, you get a tree of traces, a trace tree. This example tries to explain this concept. Well, it's another example which is very, very easy, of course. We have a loop which runs for a while, but inside the loop there is this if. It means that, and the code path taken, well, is different every time we iterate, because for odd numbers we do something, and for even numbers we do something else, which is completely, which violates our first assumption. The first assumption we did is that a loop is likely to take always the same code path. This is a completely different example, but we meet it in real code. So we need to be prepared to produce efficient code for it. This is the trace for one code path inside the loop. We execute the loop, we detected that it's hot, we traced it, one iteration, and by chance it was the iteration that contained the multiplication. That's why I put it in red. And also note that there is this guard, which is very important, because it's the guard which will fail very often, because we do an iteration, then it fails at the next one. Then we do an iteration again, and it fails. So what happens? We enter the trace, we compile it, we have the code, and then we execute. We arrive at the end of the execution, we jump back. This is the trace, but you really have to think as it's the assembler, the compiled code. We arrive at the end of the loop, we jump back, and then we start executing it, and etc. And then the guard will fail, because earlier it was an even number, now it's an odd number. So this guard fails. And what happens? Well, this is some internal details of tracing JIT. I'm not going to explain it very deeply because there is no time. But we go in what we call the black hole interpreter, because now we are in the middle of the function execution. The guard failed, and we want to go back to interpretation. But we can't just start the interpreter again, because the interpreter, there is no state for the interpreter to start. We want to rebuild the state as we are in the middle of the execution of this particular code. I have some points where the interpreter can start. Here we are probably in the middle of the execution of some bytecode. We can just jump to the C code there and hope that everything works fine. So the black hole tries to fix things, to continue a bit until we arrive at a point where we can rebuild the state and enter the interpreter again, which is exactly what happens. The black hole is very slow, but it usually runs for a very small time frame. Then we go back to interpreter, and now we can start to interpret the loop again. We do it once, twice, 3 times. Then at some point we realize that the code is already compiled, and we jump to it, the assembler code, and then it happens all the same. We execute it, we jump back, then the guard fails, black hole, interpreter, and etc. After a while, the guard becomes hot, so we compile it, and instead of going to the black hole, we just compile a new executable code. So this is the bytecode for the I+1 path, which increments it. And then we have to connect it back to the loop, to the original loop. So at the end, when everything is warmed up, we have this situation in which we have the main loop, which works well for one particular case. When the guard fails, we go to this bridge. This is the technical term used in PyPy. And then at the end of the bridge, we go back to the loop. And then here we are happy. We have very fast code and no more interpretation, and everything works fine. So this was a very briefly overview of tracing JIT. There are many more things to explain, and but I hope that you got the general idea of having the interpreter, doing the trace, which is a very concrete. We compile, we execute for a while, we compile more, we connect all the pieces together, and then at the end we have something which sounds magically fast. In this second part, we will try to go a bit deeper in the concrete case of PyPy, how PyPy implements this tracing JIT concept. So we start from the EuroPython code. As I said, the PyPy Python interpreter is written in EuroPython, and well, it's a normal program which contains the logic to execute the Python bytecode. These three boxes represent some EuroPython function. For example, there is a function which implements the load global opcode, the store fast opcode, the binary add opcode, and etc. These are compiled and etc. And at some point during the compilation, the EuroPython function goes to this special block, which is called code writer, which builds a representation, an internal representation of the logic inside the blocks. And this is what we call the JIT code. This JIT code plays a bit the role of the Java bytecode we saw earlier. So to draw the parallel, this is like a bit if it was Java code, and this is the Java bytecode. Of course, we have EuroPython. EuroPython doesn't have bytecode, so we had to invent our own intermediate representation. And the operation inside the JIT codes are at the level of C, more or less. You can read them, but the operation are really get the field out of the structure, take two integer like machine words and add them together, or allocate some memory and create an object and set a field of a structure, etc. All of this happens at compile time. Then at runtime there is the meta tracer, which is the actual JIT, the JIT compiler, which uses all the information which is stored in the JIT codes to actually do the trace, record it, and etc. So we have the PyPy interpreter, which is the EuroPython code, which executes our EuroPython program. Then, when the loop is detected to be hot, the meta tracer kicks in, and it's executing the JIT codes. It's really like interpreting the JIT codes. And while we execute one after the other these lines, these opcodes, we record them. This particular step is very slow because it's like interpreting a CPU, more or less. We are really at this low level, but we do it only for one iteration of the loop. Then, after we have this very, very long trace, we can give it to the optimizer, and the optimizer does a wonderful job. It really takes a trace which is so long and it reduces it to 2 or 3 operations, which is what we can then compile. We send this optimized trace to the backend, which emits the assembler code, we execute it, and we are happy. How does the PyPy trace look like? For example, we have this very easy Python code. This is up-level Python. This is the Python you write as a Python user. You have a function, you take 2 variables, and you store it on a local variable. So the bytecode for this function is this one. We load, well, there is a typo, there should be lowercase, but okay. You load the variable A, which is a global, the variable B, which is also global. You add them and you store it in the C. The variable named C. And then when the meta tracer kicks in, it really executes this load global. So load global is this box, and the JIT code for load global is composed of these operations. So we execute it, and we record in the trace. Then we execute load global B. So we record yet another time with the operation in the load global. There is a typo here because I just did copy and paste. Sorry. Of course, the variables should be named differently because in the trace P0 is strval, like P1 is the variable which contains the name A, the string A, to load the global, and of course in the first part you load A, and the second should be B. But okay, sorry for the typo. Then we we record a binary add, and in binary add it happens the same. It happened in the Java example earlier, because if you look at the code here, you see that in binary add we have promote class, which basically is the equivalent of what we did earlier in invoke virtual. We check that P0 is of class, is the right class, and then we do the addition and we check for overflow, because in Python you need to switch to a long in case the addition overflowed. But we don't want goTos in a trace, so all these conditions become guards. We'll talk more about guard class and guard not overflow later, but yes, I mean, they are guards. And then we record the implementation for the store fast bytecode. And this, well, you get the feeling that the trace gets very, very long, and it's very, very dense of information, and it does a lot of stuff. But then the optimizer kicks in and does its wonderful job. On this slide, I just present some of the optimizer steps we have. They run one after the other, and they really do its job on top of what the other optimizer does. And so we have optimizations for removing bound checking on integers. If we know that two integers are less than a certain number, we do constant folding, which is very important. If we always have int add of 2 and 3, well, we already know the result, which is 5. We have virtuals, which removes allocation. We will talk about it later. And we have other optimization that we add whenever we have a need. So let's start from some example optimization, like Intbound. We have this example, which is very, very easy. Again, this is up-level Python, the Python you write. You have a plain normal while loop, which increments a variable by 2 every time. So when we execute it, well, it interprets and the loop gets out, and we trace and etc. And we get the unoptimized trace. This is an excerpt of the unoptimized trace we get, and is the trace? I mean, it's for the implementing this line for adding I and 2. So sorry. It's of these two. Oops. It's of these two lines, because we check the condition of the loop and we increment I. So this is the condition of the loop. We check that I15, which is a random variable which contains the value of I, is less than 5,000. And we insert a guard, because in case, well, the condition is false, we want to exit the loop. And then we have the addition, and we have this special operation, int add of, which also checks for overflow. So when the backend sees this operation, it needs to emit the assembler code for doing the addition and to check for overflow, which is a bit slower than just the addition, of course. And then there is a guard which checks that this operation didn't overflow. But the Intbound optimizer is smart enough that it sees that if we have I15, which is smaller than 5,000, and we have 2, well, we will never overflow this particular operation. So we can just remove the check. So int add overflow becomes int add, and we remove the guard. And this is essential to get very fast code for numerical examples. And this particular optimization works more often than you might think, because this is a very simple example. But for example, in the trace you can have somewhere the information that the variable I is less than 100, and this particular array is at most of 50 elements. So you don't do bound checking for when you try to subscript an element. And the information about these bounds propagates all over the trace. So even if you don't think about it, maybe there is this information somewhere, and the optimizer is smart enough to get it. Then virtuals. Virtuals is very important optimization. And look at this new example, which is very different than the one before. Yes. And okay, what happens in Python? You know, in Python everything is an object. So 5,000 is an object, 2 is an object, and the result of e plus 2 is an object as well. And what happens in CPython or in PyPy when you interpret is that every time you do some operation, you create a new object. So you have this int object which contains the value 10. This int object contains the value 2. You fish the value 10 from here, the 2 from there. You get 12, and then you allocate another object which contains 12. This is very costly, so we have an optimization that tries to avoid it as much as it can. So what do we get in the trace that for this particular case? Well, when we have the addition, like the I plus 2, we want to know what to do. I mean, I could be some whatever object. So we check. In this particular case, is an integer, so we get the class. So we know how to, and 2 is an integer as well, because it's a constant. So we know how to add the 2 integers. It's easy. So we just fish the integer value from this object in memory. We compute the result. We create a new object, and we set the intval field of this new object to the result we just computed. And the visual optimization recognizes that this object is just, we create it and we throw it away very soon, because at the next iteration of the loop, we have this newly created object. We just put this value inside, and then we fish it from it, and we use it to compute the new value, and we forget about this object and we create another one. And it's a waste. So the visual optimization, just throw it away and remember that we have this value containing the actual integer value around, and we don't need to actually allocate the object. We keep it in a virtual object, which is never allocated. And this is all done inside the optimizer. And then at the end, what we get is that, well, the information is just stored in a variable of the JIT code, which means that in assembler it's a register, or on the x86 stack. So at the end, we don't create at all this object, and we get this very fast code that you just keep adding the value to the register in memory. This is probably the most important optimization of PyPy, because it works for tons of cases for objects, but for example, if you want to call a Python function inside a loop, well, in CPython you have to allocate a frame, which is a huge object, and then all the variables are stored inside the frame in some list. And wherever you want to store a value in a variable, you have to take the frame, you take the list, you put the variable inside, and whenever you want to read it, you have to take the frame, take the list, and get it. And in PyPy, all this structure is virtual, which means that it disappears in the trace, and you just take the value from which is still in memory. Next optimization is well, another important one. All of them are important. Yes, I know I'm repeating myself, but they all do a nice job together. Is constant folding. So this is yet another example, which is very different than the one before, yes. Well, you already know about it. So what happens? Now we concentrate on this particular part of the example, the 2. Well, what is 2? Is we have the code object, which has constants stored inside. And one of these constants is a int object whose value is 2. And in the trace, when we do all the work, the unoptimized trace, which is very long, we just fish it from the code object. We have this constant value, which is a pointer to this object, and there is this get field pure operation. We just takes the value from it. Get field pure is a special operation because it means that we as PyPy developer marked this object, wint, to have a field which is immutable. So the int_val field will never change the value when we during the execution. So it's a pure operation in the sense that if the operand is constant, we can just constant fold it exactly. So what happens? Well, we just constant fold. So we remove the operation from the trace, and remember that the trace is very concrete, so we know the value of this I2 because we recorded it. So we just take this and we will substitute in the optimized trace, and so we get this nice optimized operation. Somehow the constant folding optimization finishes the job which is done by the others, for example the virtuals, because by itself it doesn't do much, but as soon as you have virtuals, then a lot of values that were not constant, they become constant because now they are known to the optimizer, and it works very well with all the other optimization, and at the end all together plays to give you the optimized trace, and it also does the more boring constant folding you could do it statically. It just happens to work. Finally, we have out-of-line guards. Now, here, the example is really different than the one we had before. Because instead of having the constant 2, we have n. N is a global variable. And this is really different because if earlier we knew that 2 is a value and it never changes, now n could change every time. So in theory, you have to write a code, some assembler code, that every time try to look up the global dictionary and find the value of n. But this is very inefficient because, yes, in theory it could happen, but usually it doesn't. So we we took an existing concept of out-of-line guard, which means, well, let's pretend that this value never changes. And we in the trace, we don't, we just treat it as it's constant. But then, during the normal execution of the interpreter code or the JIT code, we insert checks here and there to check that this value actually doesn't change. So if it happens that the global variable n is changed by somewhere else in some completely unrelated piece of code, well, we know to mark this assembler code as invalid because it's assumed that the value of n is 2 and we changed it. So, well, this is what happened in the optimization. We have this, in the JIT code, this declaration that val is, well, it's what we use internally for representing the global dictionaries. It's quasi-immutable, and then we have a guard which says guard not invalidated. Let's check that is still valid. And in theory, we cannot optimize this get field pure because P0 is not constant, but we pretend it is. So we leave the guard not invalidated and we optimize the get field pure as we did earlier. And then, of course, when it happens that we change the code, well, this optimized piece of code is just thrown away. Well, basically, we had to invent this feature because Python is even too dynamic to do some optimization, but we just decided we don't care that it's too dynamic and we optimize it anyway. And the cool thing is that out-of-line guards are very cheap. They don't have any assembler code associated to them. It's just out-of-line information which is to invalidate. And we have to thank Mark Shannon because a couple of years ago we were listening to a talk about HotPy in Birmingham, EuroPython. and he talked about this concept. And it was the right point in time where we were looking for some idea to solve this problem. We had this idea in mind, but thanks to him, we really have managed to discuss and invented the name, so it's credit to him. Finally, I want to talk very briefly, because I think we are going out of time, about a particular guard that you looked at before, the guard value. Guard value is different than the other because all the other are binary. It's either false or true. The guard succeeds or fails. Guard value means that for every different value you see in the trace, you want a different code path. And we use it to specialize the code for this particular value. But value could be whatever, like a pointer. So, for example, you can say if these two variables are both integers, like their class is this particular object in memory, which is in the integer class, we want a code path. If they are floats, we want another code path. If they are string, we want yet another one. We have to make sure not to over-specialize the code, else you get tons of code paths that are too many and not optimized. And we use it, for example, for types, or when calling functions to check that we are really actually calling a concrete function, etc. This concept is called promotion, and yet is one other very important concept of PyPy. So the conclusion is that PyPy is cool. Any question?
Yeah, wait.
The concept of these out-of-line checks.
Yes.
Could you apply that as well to classes? If you have a class, then it gets, usually it's immutable, you don't do anything fancy with it. And
we use out-of-line guards for in a lot of places, and classes is one of these. So even if you have an attribute on the class, well, usually we assume that if it's a value and not a method, or yes, there is more logic, okay. But yes, we assume that methods in the class are constant, that they don't change. So we just look it up and constant for them. And then if you change the dictionary of the class by changing the method, well, we throw away the assembler code, and then we will have to compile it again, but it's fine. And we have special logic for values like a counter. If you have a counter on the class, okay, to count how many objects there are, etc. Well, the first time it invalidates, but then we realize that we are invalidating too often. Then we add a special indirection so that the value is stored outside the class. I mean, from the Python programming point of view, this doesn't happen, but inside we have an indirection, so we can keep still the old class, but the value is looked up somewhere else.
What's the overhead of these tracing and optimizing algorithms in comparison to savings it brings? And does it make any savings in terms of time of speeding up the code?
You mean save the JIT code and so to reuse it the next time? No.
No, so what is the cost of all these algorithms you're running live while the main program is running in comparison to what they save, like when you make the optimizations?
Okay.
And is there any sense in maybe having this JIT code compiled to something lower level to make the overhead even smaller?
So the first question is, if I understood, what is the trade-off between the time spent in JIT in compiling it and then the time you save by running it? Well, PyPy is fast, so yes, it's a good trade-off. But yes, tracing is very slow, and it's something we should work on. And optimizing and compiling it is also slow, which is also a problem because it means that we have a huge warm-up time. So if your program just runs for half a second, probably it goes slower with the JIT than without. But as soon as your program runs for 3, 4, 5 seconds, or minutes, or hours, then after a while you get all fast code and you are happy. And the second, I didn't get the second question. Sorry.
Yeah, so could it be possible maybe to compile these crucial parts of the JIT itself?
Well, the JIT is written in EuroPython, the meta tracer, and it's in EuroPython, so it's translated to C, so it's already compiled.
Okay, yeah,
so
that's what I was thinking.
Okay, two questions. One, Python 3 adds type annotations to the language, and they're not used for anything right now. You guys are already doing type inference, but I was wondering if the type annotations would give you anything extra once you guys support Python 3.
Probably not. What?
That was easy. Okay, and in
No,
another...
even if there are type annotation, when we want to execute the code, we still have to check that the types are correct. So
it doesn't help
check
you.
anyway. So yes.
It doesn't help you. Okay, and the other question is, in a previous presentation at EuroPython about PyPy, you guys said that you simply cannot remember any previous trace JIT output from previous runs. You have to do it fresh every process. And I was wondering if you could say very quickly why that is, because obviously that would be a big speed up if you could cache that.
Yes. And well, it's a bit technical, but trying to explain in 2 words. When you have a trace, as I said, you have a very concrete trace. So wherever think in C, you have pointers and structures around. So you have a pointer to this object in memory, which is a value like 1, 2, 3, 4, and then if you save it and you reload, 1, 2, 3, 4 point to somewhere else in the memory. So to save it, you should implement a linker, a loader, but maybe this object is different than the object you have now. So you really can't.
I missed the part when you explained how the out-of-line guards are supposed to work. Missed the part. You didn't explain it. How they are supposed to work.
I mean, in the assembler code or in general?
What do you mean in the assembler code or in general?
I mean, out-of-line guards work by not inserting the guard in the assembler code. The assembler code just ignore it. But then we have special code that checks that this particular information don't change. Like for example, you have an object and we mark a field of the object as being quasi-immutable, which means that when we read the value out of it, we record that this particular piece of assembler relies on this field of this object to be constant. And then we have checks everywhere that if you set a value on this object, well, you invalidate the code.
Fine.
I can see you. Oh, that's better. I'm out of the university for a couple of years, but all the things that you told about today is close for me how processors work in a sense of doing the assembler work, yeah? Not really.
I don't get the question, sorry.
It's not a question, it's like introduction. It's like when CPU is making instructions of assembler,
yes.
Nowadays processors, it makes a predictions of how the code will be done. So you're doing something similar.
Well, yes, but at a much higher level.
So the question is, did you thought about or think about using the CPU algorithms for what you do?
I don't think we ever thought about it, but I'm not sure they are directly applicable because it's really a completely different level and completely different constraints.
It's like, I don't know, it's the question to you.
What was it? Oh.
How do you generate the promotion heuristics? Or how do you determine how hot is hot?
What?
How do you determine when hot is hot?
The threshold. Okay, it's configurable. Like the, I think that nowadays is like 1031 or 37, yes, obviously. And well, it's just some heuristic we did, and we saw that with this particular value we get usually good code. But you can tweak them by using PyPy --JIT, and then you can.
Well, how did you come up with 1037? Just.
Well, I think at some point it was like 1000, but then we didn't want. I mean, it's a normal number, so it might be that you have a code which runs exactly 1000 times, and then we don't want to trace just the last iteration and to end. So we wanted something more.
Does it make your benchmarks look good?
Well, of course we optimize the threshold for our particular benchmark, but the good point is that our benchmarks try to be representative of a normal Python application. So, but yes, you should, if you really care about all possible percentage of performance, you should tweak a bit with the threshold and try. Actually, at some point I tried with the PyPy translation toolchain, and I concluded that our are really the best we could. So.
You have talked about the code paths that you generate. How do you define a code path? What kind of information defines a particular code path, and how works PyPy?
What do you mean?
At the beginning of the your talk, you talked about the code paths that
yes.
the CPU follows. How do you generate these code paths? Well, I mean that you have different kind of generated code by the JIT against type information. I don't know.
Well, I mean, code path could be for every time you have an if. In your EuroPython code, you have two code paths. Or every time you have a call to a function pointer, like a virtual method in a class, you have more code paths. And we don't generate them; they are just them in the code.
Okay.
Just follow them. Yes.
About the threshold. Since the black hole interpreter is even slower, does it make sense, or do you have a smaller threshold when when you recognize that the code that is going through the black hole interpreter is hot?
Well, yeah, actually, we have different thresholds. Like for detecting hot loops, we have this 1037, and for detecting when a guard is hot, is like 200s. Or some value there, PyPy JIT -help tells you. And yes, then there are tons of thresholds, like something else we didn't talk about is when the trace becomes too long. So if it's too long, you abort the tracing, and then you can configure this threshold as well. So,
thanks.
If you keep tracing code as it gets hot, eventually you're going to have lots of traces and run out of memory. So how do you manage that?
It was a problem in some older version of PyPy, and now we have a mechanism to remember which assembler code has been executed recently and which has not. And so if some code has not been executed for some time, we just throw it away. And if we are unlucky and we want it again, we just recompile it.
I saw that there are several optimizations. Is there like an order in which you do an optimization?
Yes, it's important because, for example, you need to do constant folding after virtuals, else you don't have anything to constant fold. And yes, you need to be very careful about the order, and because to enable some, you need someone else.
Well, how do you know? How do you know which order is it? Like
well, we just designed it to be this way. Okay. But, and also we have a lot of tests about optimizations, even both unit tests and PyPy JIT test. So we actually check that if we pass this particular trace, we get this optimized trace. So if by chance we change the order of optimizations, then the test is failing and we know.
Unfortunately, we ran out of time. I can hear you. You're really hungry. So, yeah. Now, thank you, Antonio.
Thank you.